Hi, let us take a look at this problem. So we start off, before we do our equation of motion, we would like to draw the free body diagram. So I've outlined the general free body diagram steps, where the first step is you have to draw forces on the spring according to the assumed direction xt. Okay, so you can see xt here is going down, and then you have to draw action reaction forces on the pulley and the mass. So that's what happens. So you can expect if this one goes down, then obviously maybe the K has to go this way, and the pulley will turn that way as well. So if you want to write the free body diagram, so the K will go like that. Okay, and then take note that the mass is not connected at 4R, but it's rather connected to the R here. So let's say oops, okay, so now we draw there is a force or a cable connecting to the mass, so I just assume that it is going downwards in this case, so the action reaction would be going upwards on the mass. So because in the first instance, in this case, let us assume that we have an effect of mg there. So here we have action reaction from the K. So I just put it as kx1. So take note that this is a rotational and translational forces. So you can expect that instead of defining at the displacement in terms of x, you have a relationship between theta and also x. With mg in place, so I assume that I define a displacement theta dot, where it is basically the displacement or angular displacement due to mg. Okay, that is the initial displacement. So after this displacement theta, there will be the actual displacement of theta. Okay, so displacement theta, I define it as displacement after the effect of mg. So if you want to actually draw it, so maybe I can draw here with a different color. So let's say this is the point of rotation. So I can draw the displacement of this K basically take effect due to the mg. Let's say I call it theta naught, and then after that there'll be a displacement due to theta. So basically in terms of the triangle relationship with x, so basically your x1 is the combination of theta naught and theta. So I can define as x1. So this is your x1. So x1 is equals to, and the radius is 4r here. So x1 is equals to 4r theta naught plus theta. Okay. So that is the definition, so that we are clear. So theta naught is based on the mg. So we can write now the equation of motion. So your equation of motion is based on these two main masses and moment of inertia, basically the mass and the pulley. So the first equation, you can see that it's in between, you write based on the mass. So for EOM, you have to write the equation based on the mass, and the J or J naught. Okay, so we call the pulley as J naught and the mass as M here. So the way to write it, you always have a positive. If you want to write for the mass, so you write it in terms of positive, mx double dot equals to summation of forces. So then how do you actually write summation of forces? You have to get the positive is according to the direction of your x. So that's why positive is going down. So from that equation, the forces, there are only two forces here, mg and t. So the way you write it is you have mg, okay, minus t. So you have the first equation. So let me just call that A, equation A. And then you have the second equation. So the second equation will be based on the J. So the way we write it is J naught, or the pulley, theta double dot equals to summation of moment. So don't forget, this is the summation of moment. So you have to determine the direction, positive direction. So you have to follow the assumed direction x as well. So this will be the positive direction, which is counterclockwise. Okay, so the counterclockwise is like this. So that will be our assumed positive direction. So if you look at here on the pulley, T is going down. So if you actually go from the point, or from the pivot point here, okay, to this force here, so you can see that it's counterclockwise. So maybe I can draw. So from here to here, it's counterclockwise. Same. So that would be positive, but the K, it's actually clockwise, because that point here to this arrowhead is clockwise. Yeah. So maybe we can write now. So the T will be counterclockwise, will be positive. Don't forget, T is actually your your force. Okay, just pick up. So you have to times with your R. Okay, whereas your kx1, now we have to write it in terms of this expression. So you have k x1 will become negative, because it goes to the clockwise direction. So you have negative k. So you have to write in terms of x1. So you have k times 4r theta naught plus theta. Alright, so there are only two moments in this case. Don't forget, this one is actually forces. You have to times the distance, perpendicular distance, which is actually 4r. So you have to times 4r. Okay, if I can just label here. So this is force, this is times distance. So this one is actually force, this one is actually distance, so that you know your moment is force times distance. Okay, so now we have these two forces. So basically you have these two forces. If I can write that again, now you have these two equations, mx double dot, which is equation A, equals to mg minus t. So you have the t terms there that you can actually merge equation A and equation B, isn't it? So if you rearrange, so your t will become equals to your mg minus mx double dot. Okay, so you substitute from A, substitute this, okay, into B, so that you will actually cancel out the t term. So B, you can write your B, J naught theta double dot equals to T, which is mg minus mx double dot r minus you have your K for R. So this will become 16R. 4 times 4 is 16R square. And then you have your theta naught plus theta. So notice now we have the term x here. Mg. You have the term mgr. Okay. And you can actually write your mgr, okay, in terms of your theta naught. If you can actually substitute. So basically just now we have defined your theta. Okay, just now if you look at here, if you write this small here, theta is also related to your x, r theta. Okay, so if you look at this small triangle here, your x and theta, the relationship will be x is equals to r theta. So you want to write everything in terms of theta. Okay, and also you want to express all your theta naught as well in terms of mg, because you will need to cancel out your theta naught and mg. So as I said previously, if you look at the relationship between mg, okay, we start with that first, yeah, your mg and theta naught. Okay, how do you relate that? So you can see here is your mg, your theta naught. As you move your mg, then due to the mass and the gravity, then you will move theta. So the relationship is basically your, if you write in terms of moment mgr, so there's another relationship. Your mgr is basically equals to your k times 16. So basically your kx square just now. So you have your 16r square times theta naught. Okay, because the effect of mg, we have defined it here, is the displacement due to mg. So as you have this mg, it will move theta naught. And if you look at this triangle here, it is related to your 4r theta naught. So in this case, we write in terms of moment here. So mgr equals to k times the, basically this is your kind of like x naught. So when you rearrange this, you will get theta naught is equals to mg over 16 kr. Okay, because you actually cancel out one of the power there. So now you can substitute everything. Okay, we have the term theta naught. Okay, we also have the relationship of your x equals to r theta. Okay, and then you also need to substitute your x there. So your x double dot is equals to your r theta double dot. So you have to substitute, yeah, everything here. So what do you get now? J naught theta double dot equals to your mg will become everything will become your theta here. So basically if I just put here mg r minus m, so x double dot will become r square theta dot minus your k 16k r square, your, then you will have theta naught will be 16 kr plus your theta plus your theta. So you can see there's the mg term here where you can actually minus that. So your mg here minus you will left with mgr. So at the end you will have j naught theta double dot equals to, you can see that mgr will actually go away. So you have your negative mr square theta double dot. So this one already cancel out here with this term. You still have this negative 16 kr squared theta. Then you would have your, if you bring the terms together, all the theta together, okay, then you have this. Then you can write back your equation here. J naught plus mr square, everything theta double dot. Okay, so you can bring everything to the other side, yeah. So plus 16 kr square theta. Okay, equals to 0. So you can also, so this is actually the equation of motion. Okay, if you want to write, so this is actually your EOM. Okay, at the same time, if you are asked to find the natural frequency, so you can also write your natural frequency, because this represent equivalent J, this represent equivalent K. So your natural frequency, okay, is equals to square root of K over M, which is 16 kr square divided by J naught plus mr square. Okay, so that's all. Thank you.